To understand why this mill exists at this location, we need to roll back the clock by a century or so. In 1928, an Illinois dentist named William Mark Muchow came to Colorado, supposedly looking for a gold source that was suitable for use in dental fillings. Rumors of such a source led him to Quartz Hill near Central City, where gold tended to occur with a smattering of silver in the same ore bodies. When the resulting alloy exited the smelter, it had a few percent silver content and a paler, whiter hue compared to pure gold. Quartz Hill lay near the center of what was known as the richest square mile on Earth. Countless diggings had occurred in this area for over 50 years, and in the late 1920s there were at least 40 overlapping claims and 300 plus mine operations on or around the crown of the hill. These had given rise to the nickname The Patch, possibly after the patchwork quilt pattern these formed on the claim maps. At this point, the high-grade, weathered surface deposits had mostly played out, and continuing development on Quartz Hill had stalled since most of the owners couldn't afford to mine the deeper, lower-grade ores and fight court battles at the same time. Muchow assessed the patch and realized the hill was ripe for consolidation. Using the smooth banter and showmanship of a skilled salesman, he soon convinced the competing claim holders to be relieved of their legal and financial troubles by selling to him, upon which he consolidated his operation under the colorful moniker the Chano Mines. He then signed on a roster of investors to fund his new project. Muchow was dreaming big. Quartz Hill's core was once the main vent of a prehistoric volcano, which later filled up with quartz and brecciated hydrothermal deposits. So, he set out to unmake the geology in reverse of how it formed, by tunneling horizontally below the surface, and then collapsing the entire crown of the hill down into that tunnel, one big explosion at a time. In miners' parlance, this was called a glory hole operation. The task of processing all that ore would eventually require 3 separate mills in succession. Since Muchow had access to the Argo Tunnel and its electric tram via some of the Quartz Hill mines, he initially bought the Argo Mill in Idaho Springs in late 1928, and used it for a year while getting his local operations in order. The first local mill for the Chano Mines then opened in late 1929 and operated on the east side of Quartz Hill until the early 1950s, when the tailings discharge pond and pile grew so large they posed a genuine risk of burying Central City's main intersection. The second local mill was then built on the southeast side at the mouth of Virginia Canyon and entered full operation by the mid-1950s. It continued operating under Muchow until his death in 1969 and was then run in a fluctuating state by his successor, Harold Caldwell, until the 1990s. The first mill is long gone, although many photos of it remain in circulation. The second mill is still standing, but not for much longer unless restoration efforts are undertaken. Water and gravity are a powerful team, and most old mills relied on both for efficient material transport. The same forces that scoured this ravine from under the mill's abandoned supply pipe were used to lubricate the mill's grinding processes, transport crushed ore as a slurry, and enable froth flotation and gravity separator machines to finish removing both sulfides and free milling metals from the ore chunks that first exited the earth and entered the front of the mill. The chain of mines had at least one pump house down by the river, somewhere near the dividing line between Black Hawk and Central City as near as we can figure. We assume water was pumped across the hill through this spiral welded steel pipe and then stored in the nearby retention pond. The pond sits about 75 vertical feet higher on the hillside than the main mill across the road, so a quick hand calculation suggests that a drain pipe in the pond would provide water pressure of about 30 to 35 psi at the mill, which is enough to run a functional water system. To make sense of everything we're seeing in here, which looks like little more than a jumble of motors and belts when viewed up close, let's create a process flow diagram showing all the major equipment involved in the dry pre-crushing stages. We'll colorize equipment by type, then add brightly colored identification numbers and arrows to show how ore flows through this step. Item 1 is a belt-style ore feeder. It pulls large blocky chunks of ore blasted out of the mine down into the primary jaw crusher, which is item 2. These exit at a size that is much smaller than before, but still too large for the main mill. So, a transfer belt moves the ore stream to item 3, a simple hopper that bypasses a location where equipment was removed at some point, and another transfer belt carries the stream up to item 4, which is the secondary jaw crusher. 2 more transfer belts then lift the ore up into item 5, a vibrating screen. Any material that passes through the screen just drops through, and any that does not is given a final pass through item 6, a gyratory crusher. The discharge from both 5 and 6 is now at a small, consistent size, ready to be transferred to the ore bin at the main mill, which we will examine later. The discarded equipment here is another type of gyratory crusher. It works on the same principle as the Simon's crusher installed in the mill, but the bearing here is located at the top rather than the bottom. Just downhill is the motor that probably drove the unit, partly disassembled and scattered about. It might seem strange that the mill owner would have pulled this equipment out of the process and not resold it to another mill or at least a metal scrapper. Consider that the crusher unit is mostly a large chunk of cast iron and probably weighs at least 40,000 pounds just sitting there. It may have been more expensive to haul it away than to just let it rust. We never did figure out why this rotary screw compressor was stationed back here. The drive motor is rated 75 horsepower, so it was no slouch. An air tank did turn up farther down the hillside, so it may have just been a shop air source rather than being linked to a specific process step. But the compressor seems a bit large and specialized, so we're probably overlooking something. A couple hundred feet east of the pre-crusher building, we located the original electrical service tap. Although disconnected, there is still overhead service equipment and a couple outbuildings, but any transformers and switchgear are long gone. In the crushing house, there are two main electrical control areas, both located on the west side of the building. On the second floor, we located a few 480-volt three-phase control panels and relay controls, and a bulky, awkward-looking assembly that may have been the main contactor and soft start ballast for the primary jaw crusher. Down below, another electrical control platform provided interface for the rest of the mill. Our question is, what size utility service was required to power all this, and what did it cost to run everything? We didn't get a nameplate on every motor, but we got enough to make an educated guess. First, the primary jaw crusher motor bears markings for Crocker Wheeler and a nameplate rating of 150 horsepower. The secondary jaw crusher motor is an Allis-Chalmers unit rated for 75 horsepower. The third nameplate we found was on the rotary screw compressor motor, also 75 horsepower. We didn't get a rating for the Simon Crusher's drive motor, but based on the working load, age, and physical size, we'll go with 75 horsepower. Next, counting inside this building and the external transfer to the main mill, we have 6 transfer belts. Those motors appear to be in the range of 15 to 25 horsepower each. And finally, there are a couple miscellaneous smaller loads, including the shaker screen motor and the ore feeder into the main crusher, which we'll estimate at 5 to 10 horsepower each. Add all those together, use the rule of thumb that 1 mechanical horsepower pulls roughly 1 kilowatt from the electrical system, and throw on a few miscellaneous house loads such as lighting and control circuits, and we're looking at around 500 kVA for the source. Bulk electrical rates vary, and then there's things like demand charges and power factor penalties, but let's suppose we want to restart all this equipment and the overall cost of electricity for the mill is a very reasonable 20 cents per kilowatt hour. To run the complete pre-crusher stage near full capacity for 1 hour will cost about $100. That's just one of the routine expenses to run this mill, and that's not accounting for the additional megawatt or more that is also being drawn down at the main mill. And then there's the off-site shipping and smelter fees to extract the final products from the mill concentrate, plus whatever environmental protection measures are enforced to contain the tailings discharge. Considering all those processing expenses, it's not enough to know that there is some mineral content in the ore. it should be assayed to prove it has enough mineral content to net a profit after paying all the processing costs. If it won't pay, dump it in the waste rock pile. Hey everyone, thanks for joining us again today on what was episode 17 of HMGM, How to Model a Gold Mill in 27,000 Easy Steps. Today's episode was a part 1 of 2, looking at the final form of the Chano Mines mill. The pre-crushing building that we were in today, looking at all of the dry processing stages, is kind of deceptively small looking from the outside, but it is in fact about 80 foot long by 20 foot wide, and at its highest point probably about 25 feet tall, maybe somewhere in that range, 25 or 30 foot tall. So it's not small at all, but the mill down below where all of the wet processing takes place is far bigger still. That one in its final form had at least 4 or 5 ball mills. One of them is actually a cone mill if I recall correctly, but we'll look at that next week in part 18 of this series. So hope to see you then. Meanwhile, hope you found what you saw today interesting and informative. And remember, if you go exploring on your own, please be respectful of these properties. A lot of people aren't. There is graffiti on this one to an extent, and it looks like some vagrants have possibly been living in parts of it now and then. But in any case, it's all still there, it's all still reasonably intact, and so it was really interesting to look at, and hopefully you found it interesting to see. See you again next time in part 2. Has anyone seen my phone?